Okay, now that we're recording, I've written the test.
Okay.
Yeah. And my goal was to come up with problems that are interesting yet still doable. And also like variations of things that you've seen, whether homework problems or also examples that are in the book that I've also covered. And in other classes I've been asking about this, like I often put out a practice test, and that wasn't practical this time due to the lack of available material. Because basically it means you're making two versions of every question. But I think I can give you something that's almost as good. So I will list the exercises and examples from a book on which that are used for inspiration. So if you review those and see how they're worked out, then you should be fine for this. And no, I did not put a problem like that number 15, where you're doing 9 different kinds of integrations or whatever. There is some integration involved in the test, but nothing like that.
You expect us to be able to integrate?
Yes, I do.
Oh,
okay.
what about take a derivative?
It might come up.
It might come up. Oh my gosh.
The other thing I've done is I've made a formula sheet, which actually includes some integration rules on it, and also some trig identities and Fourier series formulas, Parsifal's equation. So I have posted the formula sheet on the site. So if you go to the lectures page and you go to where the date of the midterm, so October 10th, then you'll see the formula sheet posted there. So that way you know in advance what you don't have to try to remember. Okay. But yeah, the integration formulas there will be needed. Okay, so that's one resource, and now okay, I need to. All right, so. All right, so for the most important part of the class today. So I could say study all the homework, but there were some that I could exclude. Okay, so these exercises, so from chapter 0, it's most of them, 1, 3, 6, 10, and 13. So I left out a couple of them. Because that would happen, there are 6 problems. I'm going to list more than 6 examples and exercises. But, because the reason why is, in some cases, I took bits and pieces from 2 items to make one problem. So, okay, and then also from chapter 1, only a couple from chapter 1. For chapter 1, I relied more on the examples than the exercises. So 19 and 33. And then, actually, and no examples from chapter 0, just from chapter 1. And I number the exercises, I number the examples in the notes the same way as in the book. So you can look at either one. Okay, so 9, 11, 12, 9, 11, 12, and then 41. So that's your study guide right there. So what I would suggest, the reason why I'm telling you this now, is then you'll have time to look through them for Monday's class, because Monday I'm not covering anything new. Monday is review. So if you have any questions about these, that'll be the perfect time to ask them. But I'll also just do a general review. Well, whatever you guys need. Or if you say you're good, then we'll just go. Okay. And then, so on the following Wednesday, I'll give Dr. Zhu the tests. Oh, so you'll see a lot of you guys. Well, I heard he was going to give a test on the same day, but he talked him out of it. So, yeah, which is good because there's no way I was going to change.
So those of us in Dr. Ding's class who have a test on the 9th will just have to bear it.
So it tells me there's no way on earth he's going to change either. So, I had a situation as an undergrad where I had 3 tests scheduled on the same day, and I would ask each instructor, and they'd say, ask one of the other ones. So they got a copy. They were playing against each other. And finally, one relented. So I only had 2 to suffer through. Okay. And then, what else was I going to mention? Oh, yeah, because while you're taking a test, I'm going to be speeding down to New Orleans to the airport.
That's
because we have, assuming all goes off as planned, one of your fellow master students, Tavish, will be defending his thesis at 1 o'clock on Wednesday. So I'll be there for that. Then 2 o'clock, bam, I'm out of here. and then 3 o'clock, take test. All right, and then you finish at 4:30, then 5:30 I fly. Far away from here. Okay, because that's what fall break is for. Okay, so...
It's not a conference, it's not... It's just you want to see the back of us?
Yeah. Okay, so see what you can do with that. All right. So then, when I return from fall break traveling and get the test back from Dr. Zhu, well, there's single digits of you, so hopefully get graded pretty quickly to have back on Wednesday. Okay. All right. So any questions related to the midterm?
So no example. You already said no examples from 1, and there's nothing from chapter 2 that's going to be on this.
Right. It stops at chapter 1. Yeah. So focus is on the first 3 homeworks. Well, which I guess makes sense because I've not posted any homework problems from chapter 2 yet, even though I have a list. Okay. So. Like it didn't assign many problems from chapter 2 anyway. There aren't as many. Chapter 1 are like 40-something problems to choose from. And yes.
Please, will it be like the way we did the numerical meeting that we'll stop, we'll continue with it, we'll stop in the next time class, or it will just be the same thing?
I hadn't thought about that, to be honest. Okay. I'm open to doing something like that, like after.
Okay.
So you'll have a whole class period. Because the thing that I don't know about is I've never given this particular test before, because I haven't taught this class before. So I'm thinking, 6 problems, and I didn't really go out of my way to make them long. So, it should be fine, but I might be totally wrong, and you guys only get through half of them. So do your best. At least start each one. Actually, that's a good idea because so then when I look at them after, I'll decide because it looks if they're all in pretty good shape, then there's really no need. So because what if I make the test too short? No one's going to be bothered by that, including me. Just I keep in mind that I have to grade this.
We're learning that.
So try to be more thoughtful about that for tests than I have been for homework. I'd be fine with setting aside like a portion of a class period the week after if there's some clearness there. So it's something more based on the overall class performance. But if I feel like you guys are tanking intentionally to get more time, I'm not going to be happy about that.
Okay.
So basically you're saying if we haven't gone through each of these problems at least a dozen times, it's our own darn fault?
pretty much, yeah.
That's fair.
Yeah.
You know, I'm getting this subliminal message of sign up for PhD level courses at your own at your own risk.
Yeah.
A certain lack of sympathy here.
Yeah, that's one of the difficult things about when I have students that are taking classes where, like, taking classes that are 400, 500 levels, or mixing of undergrads, and then a PhD level class. And of course, when undergrads are present, then like, of course, you're going to be gentler on them. And then when it's just PhD level class, it's like, oh guys, come on. So there's a certain disconnect there. But unfortunately, we're required to clearly demonstrate that there's a true difficulty jump from undergrad to master's to PhD. And sometimes we fall short. Like one semester, we offered, different faculty members offered 2 complex analysis courses in the same semester. It's like 536 and 636. And some students took both, I guess. The general consensus was that the lower numbered one was the harder one. Even though that was also 436 that had some undergrads in it. So,
well, that means
yeah.
it'd be nice if we'd offer a complex analysis course again.
Yeah.
I can testify that 605 is a lot harder than 285 if they need a personal.
605.
Okay. Well, he's still not here? Well, yeah, I'm definitely going.
you know the difficulty. You know, when you have to print out something in a hurry,
Yeah.
something will go wrong.
The printer will jam, and yeah.
The printer will jam. The file will suddenly have disappeared.
Somebody put holy paper in the printer.
Oh, yeah. Yeah. Well, some of my colleagues use colored paper. So that's pretty aggravating too. Then of course they forget to take it out. And, yeah. Okay, so let's cover some material that means nothing to you now. But actually, it has some pretty important things like the Shannon sampling theorem and and the uncertainty principle, like a formal statement of it. I didn't have room for proof, but the proof's in the book. Well, depending on what material comes next, I may include it later. Okay. Filters. All right. So the idea behind filters is basically to clean up a signal in a certain sense. Like, signals, as you may know, have noise in them, and that reduces their quality. So what we do for filters is try to capture the meaningful content. Filters can smooth out the signal to a certain extent and get rid of that noise. Okay. All right. Oh God, what? Okay. Okay. Yeah. Well, sometimes when I get emails and I'm like, "What? What do you want?" Like, Dr. Schroeder. Because that means I have to dang, I have to drop everything and do something.
Well, you know, they're just those few people in everybody's life.
Yeah. So, a filter is really just a transformation. All right. So this is sections 2.3 and 2.4. Oh, actually, I guess because I'm going to mention the uncertainty principle, there was a smidgen of 2.5 too. So a filter is really nothing more than a transformation L. So the notation that I'll use is we apply. It's actually a similar notation that we've already seen for like a Fourier transform. You have the operation, and whatever you're applying the operation to is in square brackets. Mm-hmm. So we're applying to a function or signal f, and the result would be some new signal f tilde. So unlike a Fourier transform, which maps a function of t in the physical space into your function in your frequency space, function of lambda, here it's a function of t mapped to another function of t. So we stay in physical space. And we're going to only focus on transformations that are linear, just like the Fourier transform is. So the filter applied to a sum is the same as applying the filter to the functions individually and then adding. Also, scaling a function, then filtering is the same as filtering, then scaling. So everything works out nicely there. Now, another piece of notation I'm going to add that will help you later is time shifting. It's a very common thing. So f sub a of t is defined to be the function f evaluated at t minus a. So fa is what you get by taking f and shifting it to the right by a units. What that means that a is negative as it shifts to the left. But, okay, so I need that notation to describe a particular type of filter that's of interest to us. So a filter is called time invariant. If, now in words, time invariance means if you shift a signal and filter it, that's the same as filtering first, then shifting. So it doesn't matter in what order you filter and shift. So mathematically what that means is if I take a signal and shift it first, then filter, and that gives me a new function of t, then that's the same as applying the filter to the original function f, and then I shift that. So, okay. So on the left side, it's shift followed by filter. On the right side, it's filter followed by shift. So if the result of that is the same, then we say it's a time invariant filter. And that's very important because, like, can you imagine if suppose your signal is, like, it's some audio signal, let's say. You're listening to someone's voice. And so you want the filter to act on in the same way on different portions of a recording. You don't want them to like certain ones to be mashed together or stretched out, that would change the pitch of a voice or something like that. So if you don't have a time invariant filter, you might have these kind of unwanted effects. So basically, time invariant filters behave like you intuitively think a filter should. That it's something that's meant to clean things up, but not really mess with the raw content in any strange way. That's such a technical definition I gave there. All right, now I'm going to give an example of a one that is a transformation that is. Just heard from Lionel. Sent me something. It's like, well, then get to class. Okay. So two filters, one that is time invariant and one that is not. So a lot of filters are described as a convolution with some function. So convolution is time invariant. Okay. So if I start for right side of the previous equation, so what I'm doing is I'm taking the convolution of f with some function L. Remember, convolution, welcome. Please don't do that again. Convolution is commutative. L star f is the same as f star L. And we evaluate it at t minus a. So in terms of the definition of a convolution, so that'd be integral from minus infinity to infinity. We take the filtering function, and we have t minus a, that's being plugged in here, minus x, and then we have f of x dx. So, because, I'll put this off to the side, L star f as a function of t, which I forgot to write. My eyes scroll down too far in my notes. T minus x, f of x, dx. So that's the generic convolution. All I've done is replace t with t minus a. So then what I can do is make a u substitution. Let y be equal to x plus a. So that's just a shift. So dx and dy are the same, and we're integrating on the entire real line. So we make a shift, we're still integrating on the entire real line. So much of this stays the same. So minus infinity to infinity, and I still have dy out here. And this is going to be f of, well, y is x plus a. So x is equal to y minus a. And then I have L of t minus y. Okay. But this is a shift of f. So this is the same as fa of y. So if I compare this to this, that's just a plain old convolution evaluated at t. But not of f, but of fa. So here I filtered, then shifted. Here I shifted, then filtered. The result is the same. So convolution is a time invariant filter. So any questions about what happened there? Okay. So now my other example is a valid filter, but it is not a time invariant filter. Anti-differentiation is a linear operation, as you know. But not a time invariant one. So if I compute both these things, shift and filter then shift, what we'll see is that they do not agree. Time invariant. It is time variant, but that's not an actual term. Okay. Now, so the definition of my filter, L of t, is the integral from 0 to t of f of tau d tau. So it's taking a particular antiderivative, where we just fill in 0 for lower limit. So it's easy to figure out filter then shift, because all you have to do is replace t with t minus a in the upper limit of the integral. Now, if I go the other way, shift then filter, so what that would mean is integral from 0 to t, and for f of tau, I fill in f of tau minus a. Okay. So what I do is, again, I use substitution. So I let tau tilde equal tau minus a. So that way I have f of tau tilde. So this matches this, just with a different variable. D tau tilde is equal to d tau. So notice, if you look at these two integrals, here and here, so far they match. But I've forgotten one thing. I need the limits of integration. So if I plug in 0 and t for tau, I'm going to get minus a down here. And then I'm going to have t tilde, okay, it's going to be t minus a up above. So close. They all, so here and here, this is what we have to compare to check for time invariance. That lower limit is different, minus a. Now, if we knew that f was 0 for negative arguments, then on those functions, the filter is time invariant. But otherwise, no. So these do not match. So the anti-differentiation filter is not time invariant. All right, so questions about this? Okay.
Though I should ask, do you really want questions about limits of integration at this level?
No. That would make me cringe. Okay. Well, see, a lot of times, whatever level class I'm teaching, the questions often revolve around concepts at lower levels, whatever those lower levels may be. Yeah. Now, at this level, that opens up a lot of possibilities.
Yeah.
But always something lower.
Yeah.
Like when I'm teaching Calculus 4, multivariable calculus, and the most common source of mistakes are students confusing addition with multiplication.
Oh, no. Well, it's just been so long that they no longer remember what it's like to be an elementary school student.
Yeah, because when you get someone like that, yeah. One time I saw a meme featuring this. It said, every time you do this, a puppy dies. Oh, people at home can't see that. Don't do that.
Don't do that.
Okay. All right. Now, one nice thing about time invariant transformations is that even though here I just gave one example, convolution. So it might seem like there are all kinds of other possibilities for time invariant filters, and yeah, that's true. But it turns out that all time invariant filters can be described in a common way. So at least to a theorem I'm going to prove that will show this surprisingly simple characterization. But first I need a lemma that will help me. Okay. So let's suppose that L is a linear time invariant filter. Okay. And I'll let lambda be equal to any real number. Then it turns out that if I apply the filter to, let's see, e to the I lambda t, so for whatever lambda is, so if I apply it to this complex exponential, it turns out that I can say that this is equal to square root of 2 pi h hat of lambda times e to the I lambda t, that there's some function of lambda only that makes this work. So any linear time invariant filter can be described by this property, which will lead to a simpler characterization building off of this. Okay. So here's how you figure out what the function h hat of lambda is. Okay, so to prove this, and it's a pretty short proof, I'm going to define this function g lambda of t to be the result of applying the filter to this e to the I lambda t. Now, L is time invariant. We need to make use of that. So I can say that this function shifted, so here it's filter then shift, is equal to what you get if you shift then filter, so e to the I lambda t minus a. Okay. All right. Now, I'm going to break this down and write this as e to the I lambda t, e to the minus I lambda a. Now, e to the minus I lambda a is a constant. This is a linear filter. That means I'm allowed to pull the constant out. So e to the minus I lambda a L e to the I lambda t. Okay. But what is this? This is g lambda of t. Okay. Okay. So if I were to summarize, I have g lambda of t minus a is equal to e to the minus I lambda a g lambda of t. Okay. Now, okay. What I'm going to do now is I'm going to let t be equal to 0. And keep in mind, a is any real number, positive or negative. So I can replace a with minus a, and this relationship still holds true. So, and I can rename a to something else. So I can say g lambda of t is equal to e to the I lambda t. Wait, I'm going to change where I wrote this. I'm constricting myself. Where above instead of below. Okay. Equals e to the I lambda t g of 0. So this is the relationship we really want. Now, it's going to seem a little strange, perhaps, how I got this from this. What I did was I set in here, I set t equals 0. I negated a throughout, and then I called a t. So in other words, a killed t, negated itself, and assumed t's identity.
So basically, we have a mathematical version of Macbeth.
Yes. Very good. Okay. All right. It's kind of funny because my Honors 300 class yesterday, we talked about the importance of integrating humanities education with science. So that's an example of that I would not expect. Okay. So, but the thing is, this is the action of a filter. So now what I'm going to do is, okay. So, so I'm going to define h hat of lambda to be equal to g lambda of 0 over the square root of 2 pi. Now, okay. But what is g lambda of 0? That is equal to what you get by applying, using this definition here, L of this, where t is equal to 0. So it's L of 1. So in other words, it's what you get by applying your filter to the function that's identically equal to 1. Okay. So, okay, so, wait a minute. Just because t is equal to 0, so, okay, one thing that's bugging me about this is that when I set t equal to 0, that it also removes the lambda dependence. I don't like that. Because right here, the lambda dependence is not very apparent. Okay. Oh. Okay, I think what I have is a notation problem here. Because I'm sorry, I goofed. It's not that. You apply the filter to e to the I lambda t, which gives you a function of t, but then you evaluate that at t equals 0.
Okay, yes.
That's why there's still a lambda dependence, but not a t dependence. Yeah, because here, L is an operator that takes in as input a function of t, which is this, gives you a new function of t. G lambda of 0, right, that should be g lambda of 0, not g of 0. G lambda of 0 is what happens when you apply the filter to e to the I lambda t, get your new function of t, and plug in t equals 0 after. When I goofed before and wrote L of 1, I was plugging in t equals 0 before. Can't do that. Okay. All right. So because we have a specific value of t here, that's why this whole quantity depends only on lambda. So now my conclusion is that, now I have a definition of h hat of lambda. So now I can use that in here. And that describes my filter. So, so a filter applied to a simple wave, function of this form, e to the I lambda t for some constant lambda, happens to be the same function again times this constant square root of 2 pi h hat of lambda. Another way of looking at it from a linear algebra point of view is that e to the I lambda t is an eigenfunction of L, where that is the eigenvalue for each lambda. Each lambda gives you your own eigenfunction with its own eigenvalue. I don't think a book bothered to mention that, but it's a good way to look at it. So that's another way of understanding time invariant filters, as opposed to other filters, have e to the I lambda t as eigenfunctions. Okay. Now, all right. Okay. And So you can also kind of see that here, where yeah, that applying the filter to e to the I lambda t gives you e to the I lambda t, and then this is the constant that multiplies it. So g lambda of 0 is also the eigenvalue. I'm just expressing it in terms of this for a theorem. This seems like a strange form to have the square root of 2 pi there, but that's because of a theorem I'm about to prove. That's more convenient for that. Okay. So all time-invariant filters have this nice property, which allows us to characterize time-invariant filters even more simply in this theorem. Okay. Because I told you earlier, or I showed you an example, that if you have any convolution, that is a time-invariant filter. So, it turns out there's actually sort of converse to that. That under a reasonable assumption on f, on your function space, it turns out that all linear time-invariant filters are convolutions. All right, so L is a linear time-invariant filter on space of piecewise continuous functions. So we need that assumption for this converse to hold. Then we can say that the filter applied to such a function f is actually the convolution of f with some function h. So if you're talking about the space of piecewise continuous functions, not only are all convolutions time-invariant filters, but all time-invariant filters are convolutions. They're one and the same class. Okay. And that rather cumbersome proof over there for the lemma leads to a relatively easy proof over here of a theorem. Because I'm applying L to some function f, and what I do is I write f in terms of its Fourier transform. This is a Fourier inversion theorem, or inverse Fourier transform. So that gives me f hat lambda, e to the I lambda t, d lambda. And what I could do is L is a linear transformation. So I'm allowed to move it inside the integral. So now I have 1 over square root of 2 pi, minus infinity to infinity, f hat of lambda, L of e to the I lambda t. So now I can apply the filter to just e to the I lambda t. And by the lemma, I can write that. So I have 1 over square root of 2 pi, minus infinity to infinity, f hat of lambda. And now that, by the lemma, gives me square root of 2 pi, h hat of lambda, e to the I lambda t. Square root of 2 pi's cancel. Wow, wasn't that convenient? I had to force that to put that square root of 2 pi in the lemma. And
where they got that idea?
That, what's left, so the integral of f hat of lambda, h hat of lambda, I lambda t, is exactly the convolution of f of h evaluated at t. Okay. Because a convolution in physical space is the same as a as ordinary multiplication in frequency space. And hold on. earlier notes I want to check on. Okay, sorry. So that's why convolution commutative. I mentioned this last time. Okay. I want to check something from last time's notes about convolutions. Okay. Oh. Oh, right. Okay. So when I take the inverse transform of f hat g hat. Okay, normally when I take the inverse transform of f hat h hat, I have to put a 1 over square root of 2 pi out here. And then the result is 1 over square root of 2 pi times the convolution. So I was making sure that I have my scaling factors correct. And yes, I do. Things Fourier transform is written about in different books in different ways. Different scaling factors, different conventions. It makes it pain to keep track of them all. They're all equivalent, but yeah.
I think a lot of it has to do with the part of the difficulty that it's used in so many different fields.
Oh yeah.
Especially when you go between applied mathematics and engineering, you're just going to get such a variety of conventions based upon what they did, and of course.
Oh yeah. Well, that's like a spherical coordinates, math versus physics.
Oh yeah.
Yeah. So. Okay, so any questions about this? Okay, so now we have a nice way to think in terms of time invariant filters. It's always a convolution with something. Okay. Now I'm going to talk about another type of filter. That's called a causal filter. So, to explain why we need this concept of causality, let's suppose you have a signal that you're filtering. Yeah. And let's suppose that for a certain length of time, the signal has nothing in it, but it's dead air, which mathematically means that the function is equal to 0. Yeah. It would be kind of strange if when you filter it, during that period of dead air, which is going to be the same period of time because it's a time invariant filter, that you'd hear something. Yeah, but that intuitively doesn't make sense. That if you have, in other words, filtering dead air should still give you dead air, silence. But not all filters are going to do that. Depending on the kind of filter, you could have some introduction of some content before it's supposed to happen. So when it happens as you expect, that the filtering of dead air still gives you dead air, that's a causal filter. Okay. So a filter is, actually now I'm getting into section 2.4, is causal if the following is true. That if f of t is equal to 0 for t less than a certain time a, then that means that LF, so filter L of t, is also equal to 0 when t is less than a. So the output signal begins after the input signal does, or maybe begin at the same time, but definitely not before. Okay. All right. Now it turns out there's a theorem that very simply describes causal filters. Okay. So So let's suppose that L is time invariant. Now, by the previous theorem, LF is a convolution of F with some function H. Okay. Now, L is, so these are just my assumptions. So L is causal if and only if the function H is 0 for negative values of t. Okay. All right. So, and because H has content for negative time, that allows the output signal to begin before the input signal does. So if you remove that possibility, then you're good. Then you won't have noise where there should be silence. Okay. All right. I should say, when I say dead air mapping dead air, that's at the beginning of the signal. Like for instance, suppose you have silence, then you have some sound, and then silence again. Now, the silence would be silence before anything happened. That should still be 0. But then you could have, because of the content that you have following that could spill over into later periods. So I have to be careful how I phrase this. So dead air up front must be mapped to dead air up front also during the same period of time. After that, you're on your own. Okay. All right. So this is the only condition we need to have a causal filter. Okay. And that's something that you can prove using a definition of convolution. If you carry out the convolution and substitute t equals 0, t being something negative, then you look at what's happening with the integral, and you can show based on where this is equal to 0 that the value of the integral will be 0. So I don't have it written out here. It's good. I guess I found it less interesting than other things I could have included. But that's the general idea. You just work this out, plug in a negative t, show that the integral must be 0. Okay. Well, now okay. I'm halfway through the notes, but I'm more than halfway through the class time, so this will be interesting. At least none of this is on the test. Okay. Now, I'll just write quickly another theorem that goes with this one. That describes a Fourier transform of H. In the causal case, it happens to be a Laplace transform. So this is fancy L applied to your function H, evaluated at I lambda over square root of 2 pi. All that is it's just the definition of a Laplace transform, and also the definition of a Fourier transform and how similar they are to one another. And the reason why, so if L is causal, the reason why this only works if L is causal, because Fourier transform is defined as an integral on the entire real number line, minus infinity to infinity. Laplace transform only covers a positive part of the real line, 0 to infinity. There's no way those can be equal unless the function you're taking the transform of is 0 for negative t. And because it is in the causal case, that's why you can do this. I have no need for this later, but just want to mention, in the causal case only, there's this nice connection between the Laplace transform and so you can get the Fourier transform of your filtering function from the Laplace transform that they're closely connected. Okay. All right, so I'm going to have an example here. All right. Let's suppose our function f of t is given by this. So exponential and linear combination of sines and cosines. Actually, the sines. Okay. Well, actually, this product of sines can be rewritten as a sum of cosines, but I won't bother with that. Yeah.
It's so cosines just looks so nice.
But this is the important part here, with sine 40t. And with a relatively small coefficient, that's going to introduce some high-frequency oscillations that are relatively small. So if you were to plot this function is graphed in the book. The dominant part is a low-frequency curve, frequencies 2 and 4. But then you have a smaller part of frequency 40 that adds some noise to the curve. So we'd like to filter that out if we can. So I can let h of t, the function for my causal filter, be equal to some constant a e to the minus alpha t, when t is not negative, and 0 otherwise, to make it causal. So it must be 0 for negative t. Well, I'll just write that in. So then, actually it turns out that the Fourier transform of t is a over, so just for definition of Fourier transform, square root of 2 pi alpha plus I lambda. Okay. So, I'm going to choose a and alpha equal to 10. And the result of that choice is that h hat of lambda is small when lambda is at least 40. So in other words, because this is small, what's going to happen is the Fourier transform of this is going to be multiplied by this. So if this is small, for lambda at least 40, actually that would be an absolute value. Okay. Then, by taking convolution of this f of t with this h of t, this term is going to be reduced. Whereas this term is generally not going to be disturbed so much. I mean, it's going to be affected a little bit. So what happens is, since this is of a reasonable size when lambda is smaller, like in a range 2 or 4, that means that it's disturbed. So, and I believe it's shown in the book what happens before and after filtering. So you want to make sure that at frequencies that you want to get rid of, that the Fourier transform of your h is small for that range of frequencies. And that way, the filter achieves its desired effect by getting rid of the noise, but keeping the content. Like for instance, if you have someone speaking and you have background noise, you can remove that background noise and hopefully preserve a person speaking. Okay. But there's some parameters to choose, and how you choose those parameters may depend on the frequency content of the signal. Like what part of it do you consider worth keeping? What part do you want to get rid of? So it makes it kind of an inexact science. Okay. Now, I only have 20 minutes more. I may not be able to talk about both the sampling theorem and uncertainty principle, but I'll do what I can. I think a proof of the sampling theorem is quite interesting. Actually, I had planned to spend more time on the uncertainty principle, but the storm kind of got in the way of that. And it's unfortunate because I feel like I gotta cut something. Okay. Well, maybe I'll cut something else. I mean, the uncertainty principle plays a role in my research, so it's something I'd like to talk about. Okay. So this is getting into... oh, actually, I goofed. Causal filters was not section 2.4. It was the rest of 2.3. This is 2.4. The sampling theorem. All right, so that a function f is frequency band limited if f hat of lambda is 0 for lambda some value omega. So you can think of omega representing like the bandwidth. Outside of that bandwidth, f hat is 0. Okay. F to a certain range of frequencies. For example, a function from previous example, f of t. Well, actually, the exponential kind of mucks with that. If you forget the exponential, just focus on the signs. That function is band limited because outside of range like omega 42, because product of some formula, we have to add these frequencies together. So outside of a Fourier transform of that function would be 0. So, yeah. Okay. Now, here is the statement of the, it's called the Shannon-Whittaker sampling theorem. Well, I've heard about the Shannon-Nyquist theorem, and maybe that's somewhat different, but that's similar in spirit anyway. I'd have to look that up. I haven't heard of Whittaker before. It's kind of weird how things are named after people, but only certain books use those names. It's been forgotten, like poor Whittaker. I mean, everyone knows about the Shannon sampling theorem, but
but everybody knows about Shannon.
Yeah. So yeah. Well, just like Cauchy-Schwarz inequality, also known as the Cauchy-Schwarz-Bunyakovsky inequality. I've seen that in exactly one book.
Exactly one book. And let me guess, that was a book translated from Russian, right?
No, it was actually Burden Fairs.
Really?
Yeah. So we really did their homework. Yes.
No, honestly, I don't know Shannon.
What?
This is my first time hearing this name.
Oh, well, it's known to everybody in signal processing. Yeah, okay. Yeah, I wouldn't expect, yeah, it's not everybody, but yeah. Yeah, okay.
Well, everybody should. I mean, this is the modern world.
Yeah.
Without Shannon, there is no modern world. We live in a world of, theoretical things.
Okay, so let's suppose that f is band limited. With bandwidth omega. All right. Okay. So it turns out that I can write express f of t at any value of t. It's determined completely by sampling f at certain regular points. So we're sampling f at a discrete set of points, and those points alone are enough to completely determine the content of f anywhere. So I have a sum of f of j pi over omega times sine omega t minus j pi over omega t minus j pi. Okay. And this series converges uniformly in T. So f is defined on the entire real number line, a continuum. Here I've only sampled f at points at regular intervals, every j pi over omega. So points that are spaced pi over omega apart across the real number line. So a countably infinite set determines the values of a function on an uncountably infinite domain. And it's because f is band limited that we're able to do this. Okay. Okay, yeah, I think I can fit in the proof. Well, I have 13 minutes. But I found the proof in the book is a bit long-winded. My version is a bit shorter, but I think captures the main ideas. And what I like about this proof, and the reason why I wanted to include it, is that it has a very unusual idea. Because what they do in the proof is take the continuous Fourier transform and express it as a Fourier series. So it's like Fourier stacked on top of Fourier. It's your Fourier squared. I've actually never seen that before. And the reason why you can do that is because f hat of lambda is defined on a finite interval. So what we do is a Fourier series, because it seems kind of weird because f hat is already in frequency space. So we're taking from frequency space to a frequency space beyond. So f hat on the interval minus omega to omega, because that's the interval on which it's non-zero. Because Fourier series are defined for a bounded interval, and we have that here. So, and I'm going to use a complex Fourier series for convenience. So some coefficient ck, which I used alpha before, but whatever. E to the I k pi over k pi lambda over omega. So that's just a general form of a Fourier series. And now I can write the Fourier coefficients. So this is a formula for a complex Fourier series on a general bounded interval. So 1 over 2 omega integral minus omega to omega f hat e to the minus I k pi lambda over omega d lambda. Okay. Now, here's where the fact that f is band limited comes into play. This function is 0 outside of this interval, minus omega to omega. What that lets me do is extend this integral to the entire real number line. All right. Now what I'll do is note that this kind of resembles my d lambda. This is actually an inverse Fourier transform, almost. There are two things wrong with it. One is an inverse Fourier transform would not have a minus here. But that's okay, because I can write this as e to the I lambda and then put everything else like minus k pi lambda over omega. So this is like the t value at which I'm evaluating in physical space. The other thing that's wrong with this is inverse Fourier transform has 1 over square root of 2 pi out front. Here we have a wrong constant. That's 1 over 2 omega. But what I said last time about if there's something I need an expression and I don't have it, put it there. Yes. Good. So square root of 2 pi over square root of 2 pi. So the bottom one I use in the inverse Fourier transform. And the one on top just has to stay there. So that tells me that it gives me an expression for ck. It's square root of 2 pi over 2 omega f evaluated at minus k pi. Oh, I should not have that lambda there. We already have a lambda. K pi over omega. So, in other words, when I expand the Fourier transform of f as a Fourier series, those Fourier coefficients, so it's like a Fourier squared coefficients from the secret fifth dimension frequency space, whatever, are actually values of f scaled by a constant. Okay, so now what I'm going to do is I'm going to take this expression, follow my arrow, and stick it in there. So now I have another expression for the Fourier transform of f. So it's a sum. Well, I'll pull constants out. So square root of 2 pi over 2 omega sum minus infinity to infinity. And then I have this expression for ck f of minus k pi over 2 omega. And then I have this exponential, I k pi lambda over omega. Okay. Now, so now what I can do is I can take this and dump it into the inverse continuous Fourier transform to get f. Okay. So f of t, which is by the Fourier inversion theorem, minus infinity to infinity, f hat of lambda e to the I lambda t, lambda of O. Do you need a different notation? No, okay. All right. Now, I'm going to substitute this in here. But first, remember, f hat of lambda is 0 outside of the interval, minus omega to omega. So I can replace these limits with minus omega and omega. And then I will substitute this in here. So it's going to give me a big mess. Well, the square root of 2 pi's will cancel. So I have 1 over 2 omega. And then I have a sum. So anything that doesn't depend on lambda, I can pull out.
We were swapping to omega.
What? Sorry.
K was omega.
Oh, no, k still goes from minus infinity to infinity. Lambda goes from minus omega to omega. Okay. All right, so minus k pi over omega. And then what's left is the integral, minus omega to omega. And then f hat of lambda has already been accounted for, but I still have that exponential. So e to the I k pi lambda over omega. And then I also have e to the I lambda t.
Is that supposed to be 2 omega over there?
Um,
That's part of it.
Oh, that should be omega.
Okay.
Okay. Yeah, not sure how about. Oh, did that happen in notes too? No, it did not. Okay. I think I have not found a mistake in the notes today, but there's still time.
What was the omega that?
Oh, I accidentally had a 2 down here. Oh. Yeah, because I have to have a 2 elsewhere. I got to have writing 2 omega. All right. Okay, so now that's a minus omega. Okay. Now, this integral, I can actually evaluate that. And I'm not going to go through all the Cal 2 here, but, well, first of all, I can write, what?
Yeah, that's
Yeah, because I can write this as cosine plus I sine. This is a symmetric interval. Only the cosine part would have the non-zero result. So what I'm going to get is a sine. All right, so I have all this other stuff. Oh, actually, okay. What ends up happening is f of minus k pi over omega. Make sure I'm not missing anything. Well, it turns out that once because of this omega in the denominator down here, and the fact that this is a symmetric integral, because this is equal to 2 integral from 0 to omega of cosine of k pi over omega plus t, all times lambda d lambda. So that's another way to rewrite it. So that 2 is going to cancel with the 2 down here. And the other thing I'm going to get is, okay, so sine k pi over omega plus t lambda over the constant k pi over omega plus t. Yeah. And what happens is, I'll evaluate at limits 0 and omega. When I plug in 0, of course, I'd get nothing. When I plug in omega for lambda, that will help, that'll lead to some simplification. And I can take this omega and put it in here to cancel out the omega sitting in the denominator. So once I clean everything up, things get a little simpler. I'll actually go all the way to the end of class time. I have 2 minutes left. Okay. F of minus k pi over omega, and then I have sine k pi plus omega t, and down below I have k pi plus omega t. This is almost exactly the same as the expression in the statement of the Shannon-Whittaker sampling theorem, sorry, Whittaker, except k is replaced with minus j, which is fine because the sum goes across the whole real number line anyway. So that wouldn't change anything. So that's it. F is determined completely by its values at equally spaced points, and the spacing is pi over omega. So what that means is, the wider the bandwidth of the function, the more often you must sample, because the spacing decreases as omega increases. All right. And this plays a role in numerical analysis in that because you're often representing functions by their values at grid points. And if your function is band limited, if you choose enough grid points, the values of f only at the grid points will be enough to represent f exactly, which is quite nice. Okay. So unfortunately, I've run out of time. So there's only a statement of the uncertainty principle in the notes, but I'll try to find some time in a later class period to talk about that because I think it's just really interesting. And maybe I'll cut out something else if I have to, but yeah, it's a topic I like. So that's why I can do this level. It's like, I'm not going to cover that. Okay, all right. So other than whatever I do with the uncertainty principle, this actually marks the end of chapter 2. And there'll be homework coming up on that after the midterm. I'll just figure out a due date, but I'll post those problems anyway. So happy studying. So try out those things I listed, and then we'll review on Monday.